Hi, I'm Sean Mooney, professor at the University of Washington and Chief Research Information Officer of UW Medicine. Over the past 2 years, we have been creating an initiative in medical data science, and as part of that, we have created this seminar. Speakers will include world-leading scientists who will tell us about how data can impact human health and their healthcare. Please use the link below to register for our mailing list to hear about future events in this series. We hope you enjoy them.
Alrighty. Hi, everyone. My name is Bhargav Vamari. I'm a PhD student in the Biomedical and Health Informatics program. Today, I'm really excited to be able to introduce Dr. Brad Malin. He is the Accenture Professor of Biomedical Informatics, Biostatistics, and Computer Science, as well as Vice Chair for Research Affairs in the Department of Biomedical Informatics at Vanderbilt University. His research is on the development of technologies to enable artificial intelligence and machine learning in the context of organizational, political, and health information architectures. He co-directs the Health Data Science Center, the Ethics Core of the NIH Bridge to AI program, and the Infrastructure Core of the NIH Artificial Intelligence and Machine Learning Consortium to advance health equity and researcher diversity, or AIM Ahead. He is an elected fellow of the National Academy of Medicine, the American College of Medical Informatics, the International Academy of Health Sciences Informatics, and the American Institute for Medical and Biological Engineering. In addition, he was honored as recipient of the Presidential Early Career Award for Scientists and Engineers from the White House. Today, he'll be talking about how Vanderbilt University went from a bespoke data science project to building the All of Us research program, and some of the concerns around addressing data privacy at scale, what makes for good and bad machine learning in medicine, and what the future of large-scale collaborative research might look like in the near future. So without further ado, I am excited to hand it off to Dr. Malin, and feel free to share your screen.
If I can get this to work. Cool. All right. So one of the things I'm going to talk about today is a little bit about artificial intelligence. And one of the reasons why I'm going to be talking about AI is that this seems to be on the mind of a lot of funding agencies and a lot of various institutes and centers within the NIH. So AI, you have to understand, is a really large concept. And some people, when they're talking about AI, they run directly towards the concept of deep learning. And deep learning is a relatively new phenomenon, but it's not that new. Deep learning is really like the notion of neural networks on a large scale basis. But neural nets have been studied for over 70 years. Still, it's a real small corner of the artificial intelligence world. It's actually a more specific area of the more general concept of machine learning, right? Machine learning is all about how you use data to teach a computer to build a model to make forecasts. And machine learning is really this smaller subset of the bigger community of artificial intelligence. Artificial intelligence is really this notion that if you understood the ways in which the world functioned, you understood the rules that govern by which biological and physical systems work, then you could get a computer to give you that next step, give you some intuition into what's going to happen next, right? That's the whole premise of having intelligence that is not being given to you by some biological agent. But we don't always know the way the world works, which is why we end up with a lot of machine learning now. But for those that weren't completely aware of this, the notion of artificial intelligence in the medical community is really not that new of a phenomenon. It goes back at least until 1972, where this system called MySyn was developed by Ted Shortleff when he was a graduate student at Stanford. And MySyn is a really interesting concept. It was this expert system that Ted had developed, and it wasn't using machine learning. It was imagined. It was really the concept of AI at the time, which was you have hundreds of thousands of rules about the way that the world worked. And you want to use all of these together so that you could deduce what the state of a situation was for a patient. Do they have a particular infection or not? And if so, what type of infection? And this used a whole bunch of strategies that AI had been working with at the time about really what was known as like blackboard architectures, where you had lots of ideas that were, or concepts that were being built on top of one another, but they couldn't necessarily learn by themselves. And so you're always inducing this next level of information as you're coming across it. All right. So this is 1972. Now you fast forward into where we are today, and what you find is that the Office of the Director at the NIH created this working group on AI. And this, as you can read here, was established in 2018. Okay, so this is 4 years ago, and you have to ask this question of so why is it so long between this first paper in artificial intelligence and this formalization of a committee to inform the NIH, right? Now, what you'll notice if you dig into what this working group was reporting back to the director is that they hit on a couple of recommendations at their time. You'll notice, like right out of the gate here, recommendation number 2, which was build data sets that are machine learning friendly, right? And you can see that ML has its fingerprints all over this report, right? And so it's really this question of like we started to recognize that machine learning had a place in medicine. It wasn't 4 years ago, but it took a long time to get to this point. And so a lot of people have said, some people call it machine learning, some people refer to it more generally as data science. And I think it's really important to recognize that data science is one branch of AI, and at the same time, it's not AI, and it goes outside the scope of AI. And the reason why I say this is that there's a couple different things that have come together to bring us to where we are today. And one is this like increasing growth in the amount of biomedical knowledge that we have stored on hand. And as you're generating this, and as you're codifying it, you're structuring it, you're making it easier to compute over, what you see is that mathematics and statistics starts to get really interested in the analysis of this data. And when you do that, that's kind of where the field of biostatistics comes into play. At the same time, the computational sciences, or computer science more specifically, comes to the table. And this is where you see a couple of other intersections, right? And on one side, you see biomedical informatics come together when you see the computational sciences and biomedical knowledge come to the table. And then you see machine learning come into play in general when you see CS and stats and math start to interact. And what sits in the middle of all of this, that's really where data science comes into play, and biomedical data science in particular. It's when you start using all the expert information with complex statistical models and computational capabilities to do things at scale. Now, this is still not completely a novel phenomenon. This is not something that we just saw come into play like 5-10 years ago. This was something that John Takei was expecting in the 1960s in his book, The Future of Data Analysis. And for those of you that aren't familiar, I mean, this is like one of the fathers of modern statistical analysis, particularly the notion of exploratory data analysis. And we had said was for a long time, I thought I was a statistician, interested in inferences from the particular to the general. But as I've watched mathematical statistics evolve, I have had cause to wonder and doubt. And I've come to feel that my central interest is in data analysis, intrinsically an empirical science, right? And how vital and how important is the rise of the stored program electronic computer. And this is 1962, right? So he saw it coming. Right. And so as you're getting more data, you're getting more challenges. And this is why we are where we are today. Right. And these are the big V's, right? We're seeing data at higher volume. We're getting it at a higher speed or a higher velocity. It's coming in with higher heterogeneity or variety. And we have a lot of questions about the veracity. right? And this is really important. This is one of the reasons why medical records analysis or doing machine learning with the EHR data is so tricky, because you don't necessarily trust everything that you see there. Whereas if you were doing biological sequence analysis, it's a different story. You have a much higher level of trust in whether or not that A or a T is really an A or a T. And then there's this final point that I like to suggest, which is that we're now starting to see value in this data. It's not just that the data exists and we're gathering it, it's that there really is an opportunity to impart change with the information that we're collecting, whether it be medical decision-making, whether it be trying to figure out how to improve payment processes or make more efficacious and thus cheaper lines of treatment for patients. There's value that's driving this. And so machine learning, it's a process, right? This is why it has become ingrained as part of data science, where you have lots of data coming in, you're going to subject it to some black box or potentially gray box modeling system, and then you're going to come out with some relationship between all the variables that you've put into it, right? And if you don't have everything that you need on hand, or it's not working exactly as you need it to, right? There's going to be some tuning, some hyperparameter tuning, or you might find that you don't have all the data and you go back and you augment and you go and collect additional information. But it's a process, right? It's not a one-time event. So where we're starting to see, or what we have been seeing for the last couple of years, a growth in is the reuse of data that's on hand, or the reuse of environments that data gets collected for one purpose and you try and use it in a different setting, right? That's the notion of reuse, particularly electronic health records data. And that's where a lot of time where I live. And so one of the things that we did at Vanderbilt was we said, we want to let the data scientists be scientists. And what that means is take the EHR data, take the EHR system, and not just necessarily the data in the health record, and let's treat it as if it's a potentially experimental environment, right? And so let's bring the people who want to study this environment into the fold, right? Let them let them have access to the data, and at the same time, let them send models back out into practice and evaluate whether or not they work. Okay, now how do you do this? All right, so one of the first things that we tried to do was figure out how to make data more widely accessible. And the first thing one of the ways in which we did this was at Vanderbilt, we created what was called the research derivative, where we took all of the data that was in the EHR in its operational environment, and then we standardized all of it, right? We took a lot of the stuff that was even in the natural language notes and we put it into a standardized format, and we moved this into a research environment that was outside of the control of operations. And one of the reasons why we did that is that the operational environment is there to support patient care. It's not necessarily there to support data science. And so this notion of creating a research data warehouse, which is what a lot of people refer to it now, this was something that we put into effect about 20 years ago. And so that was our first way of creating. So we created a pipeline to continually pull the data out into our RDW. So as you're doing that, you have to ask this question: how do you do things in a cost-effective manner? How do you make cost-effective learning? And one of the first things that people scream for is move to the cloud. It's elastic compute. You only compute when you need it. And that's a tricky proposition. And so we didn't do this. We still haven't completely run to the cloud. And one of the main reasons is that, think about the machine learning process. So you're going to take your data, you're going to subject it to analysis, and then hopefully you come out with an answer, right? But you spend money each time you run compute. And so you pay, you get your answer. I think the first time you run your analysis, it's not going to look so great. And so what happens is that you run it again. And when you run it, you pay again. And so then you get something that comes out and it looks a little better than what you just came out with the first time. And there's tuning, and there's refinement, and there's this entire process of machine learning that I was talking about before. So you do things again, and you do it over and over and over again, and eventually you come out with something that's really meaningful, right? But you can also be in the situation where I was, where I had somebody in my lab literally blitz through $10,000 in computing credits over the course of 2 weeks. And then you're like, wait, what just happened? So this happens because, yes, we have the ability to put caps on computing, but you don't know exactly from a research computing stance how much money it's going to cost in order to do all that tuning and all of that learning in scale, and then allow people to have the scientific inquiry to explore the data and explore the models in directions that they didn't think they were going to do at first. So you can't necessarily do this. So what we did was we said, okay, well, if we're going to do this, we're going to internalize it. We're going to run it on our on-prem, and we need to make the analysis fast. And we had a lot of ways in which we were doing this. We were working in our own high performance computing environment, and at the same time, there was this company. There was this company in Netezza that was doing multi-parallel processing systems that were basically a set of blade servers all brought together with a distributed database system with FPGA chips sitting on top of all this. And we were like, oh, this is really intriguing. We wonder if this will work for doing large scale data processing. And so if you want to know a little bit more about the MPP system, we can go through this, but I just wanted to let you know, so this was built. And as we were getting interested in this, IBM got really interested in it as well. It turns out that they bought Netezza. So we ended up licensing this technology from them, and we formed a partnership with them along the way. And so what we did was we started building pipelines. We started building machine learning pipelines where you're going to do this whole process of figure out how to get your cohort, build your set of features, do your cross-validation. As you're doing that, do some feature selection, and then bring it out into a classification model. Now, as you're doing this, we figured, you don't necessarily want to do this one time, as I suggested before. So we started building relationships or dependency graphs between the various types of machine learning pipelines. And so that would allow us to cache statistics so that we could use them in different machine learning models over time. And it significantly sped up the process for doing this type of machine learning. We also looked at where was it that we could achieve parallelization. And I think that we were one of the first places to adopt Hadoop, or at the time MapReduce, for doing a lot of this. And so this was a system that was called Paramo that Kenny Yang, me, and Jimeng Soon had built and then published about a decade ago. This just gives you a little bit of greater intuition into what these types of dependency graphs look like. We ended up building this by hand because there was no simple automated way to do it at the time. I still don't think that there's an automated way to do it, but we took a little bit of time to build these dependencies, and it sped us up by several orders of magnitude. So this is computation, right? So we're like, cool, we can do computation at scale. And now this question of, can we actually put the data or get the data into the hands of who we need it to go to? Is that really feasible? So we had that research derivative. And so we've structured all the data, and then we ran into this challenge where people were asking for access to the data over and over and over again. And we're like, this is crazy. Like this, there's only so many times that we should have to support this when these are all data-driven investigations. And so we ended up creating what was called the synthetic derivative. Looking back on it, synthetic is probably not the right word to use now that we're starting to see more with synthetic data, but I'll come back to that in a second. But this is what you'll see in the literature. So it's called the synthetic derivative. And it's a de-identified version of the research data warehouse. The entire thing, all of the structured data, all of the natural language data, and we did it so that you would consistently update the same individual's record over time using a one-way hash of their medical record number. The reason why we also created this was at the same time we were creating a de-identified biorepository, and that's what's known as BioView. And so we wanted to make sure that you could bring de-identified EHR and de-identified biospecimens together for analytic purposes without having to go back to the IRB every single time you wanted to do the analysis. Now, one of the things I want to make clear, and why I said this is a regulatory issue, is that we were really probably the first place that had done this in the country, and we were really worried about what the response was going to be. And so starting back in 2004, when this was really just like an idea that we had, we started running focus groups with the local community to see if this is what they wanted. And then we started talking with patients. We sent out a patient survey, and then we started a large communications like a barrage out into the world to let people know that this was what we were going to do. So we also then, this is the whole process of just test and validate, make sure that it's working. More importantly, what ended up happening along the way was in 2006, mid 2006, we went to the Office of Human Research Protections at HHS, and we said, we're going to be using biospecimens, and we're going to claim that it's de-identified. Are you in agreement with us? And OHRP said, yeah, we're in agreement with you. And at that point, we got the IRB at Vanderbilt to sign off on this so that people could only come to access it without an IRB approval, and they would just be entering into a use agreement with the medical center for accessing the system, right? And then we went live in the beginning of 2007. We then set it up so that once that system was up and running, we created a two-tier access structure. And first, we created an opportunity for people to do hypothesis generation, very similar to what you'd see with an I2B2 type of system, or those types of general cohort query models. So people would come forward with an initial hypothesis. They'd say, look, I want people who have juvenile diabetes, they're on an antipsychotic, and there was some adverse event within the first 3 months of starting that medication. And then we give them aggregate results, counts. Do we have enough people of a certain type and for them to move forward with their investigation? But this was done without any oversight whatsoever. If they thought that there was something notable that was worth spending the effort to really dig into the data, then they would come back with their query. And now this is when they enter into the use agreement. And they might be asking for data, but they might also be asking for the biospecimen because we didn't prospectively sequence everybody. We just didn't have the money to do that because this was done on, we had medical records on 2.5 million patients, and we've accumulated biospecimens on over 500,000 individuals by now. And so we would send them back data, and then if the specimens had not been sequenced yet, we would send them specimens, and then when they generated sequences, those would come back to us, and we would build a larger system over time. Now, when we did that, and one of the questions that came out and continues to come out was, how did you handle all the natural language data? And initially, before I got to Vanderbilt, they had already licensed a system that was called DID. This was from a company that was spun off from the University of Pittsburgh. And so that's what you're seeing in this depiction here as the licensed software. And then we built around it. And we built some pre-processing software to say, look, these are protected terms. We don't want you to remove these. And then we said, there are certainly some things that you should be removing. And that was our post-processing component, right? But what was most important to the Institutional Review Board was if you're going to do this, the precision doesn't matter. At the end of the day, the recall was everything. And you needed to show that you could find as many identifiers as you possibly could so that the order of error was on the order of less than 1 in 10,000. And that was what we got to, and they let us move forward. Now at the time, that system was built on what you see to the left, mostly rules. It was lots of dictionaries, like dictionaries of patient names, dictionary of provider names, a lot of regular expressions. You can imagine that we're building on lots of lexicons and lots of rules for exclusions. And then we said, okay, well, what happens when other groups want to do what we're doing? And so that was when we started to push the machine learning component. And this was like around 2006, 2007. And we started looking at a lot of different ways to do this. And there was like, you can imagine, pick your favorite machine learning model, and you'll see since then an approach for natural language processing based on it. We built software that is still out there, open source. That was what the MIST system became, because this was a system that I built with Ben Wilner and John Aberdeen at the MITRE Corporation. This is what's known as the MITRE Identification Scrubber Toolkit. This was all based on conditional random field technology. And then we found that almost the exact same time that we were building our system, Li Shang at Emory was building almost the mirror copy of what we had in a system that was known as HIDE. These two systems are still two of the best ones that are on the market. MIST is what a lot of people like to compare to. Last year, and with a group at the Mayo Clinic and a company called Inference, we showed that you could improve upon what we were doing with CRFs, and this is mainly through just ensemble learning, and it's just how do you take like multiple models with multiple parameterizations, whether it be CRFs or deep nets, and then figure out how to bring them together in the context of transformers and ensembles. And this has kind of become the state of the art today. And this is what we're now running around the country at various places, Mayo being one of them. But no matter what you do, right? So this notion of making redaction possible in natural language text, it has its limits, right? And this is a contrived example, but I just wanted to show you like something like this could happen, where you're going to redact and there will be something that you miss, and because you are playing a redaction game, the things that you fail to redact are the things that stick out like sore thumbs. And that's what you see here with Lynn or Dr. White or 510, which in this situation was a date. And so in this situation, this is a situation where the recipient of the data can easily see where the failure is. And when we did this at Vanderbilt initially, we said, well, that's not the only problem. The other problem could be that there are semantics that exist within the data that we just can't remove. Like it might say the senator's wife or the quarterback of the professional football team. And so that was why we required data use agreements for access to this information. But then as we were working on this and as we'd started moving forward, David Carroll's team at the University of Washington, well, he was at Kaiser. He was at Group Health Cooperative of Puget Sound initially. David and I started down this path of, well, what if we took the information that was redacted and we substitute back in information that looked like real information, and what we refer to as surrogate protected health information, and would that information help obscure the information that was left in place by the redaction strategy? And this worked extremely well. And I'm not going to go through all the details here. We went through a review with humans, both at Group Health as well as at Vanderbilt. And at the end of the day, we showed that the performance it gets you to a point that we felt was on the order of like 0.99999. And it was mainly because, and what we were able to show was that you could play this game over and over again, so that you could really make it almost impossible, not just for humans to tell the difference, but for computers to tell the difference between what was real and fake, which was what we really wanted. The way we did that latter part with the computers is recognizing the potential threat of what I call a parrot attack, which is where you really start to harness the power of machine learning. And in a parrot attack, let's see if this works. What you see here on the left, let's just say this is your standard machine learning pipeline. Now, as the redactor or the de-identifier of the data, if you run your data through this pipeline and then you give it over to somebody else and you say, hey, can you tell me if something's real or fake? By looking at it, they're going to have a hard time. But they can say, well, I know what your pipeline was, and so I bet I could run the same pipeline. Now, in this situation, they run the pipeline in reverse. So instead of assuming that everything they see that looks like a real identifier is real, they make the opposite assumption. They say, well, I think your system works really well. So I'm going to work under the assumption that everything is fake. Every time I see an identifier, if I see the name John, I'm going to assume that that is a fake name. And so I'm going to tell the system to train itself under the belief that everything is fake. And therefore, when I run it to do de-identification of fake information, the things that are going to be left over are the things that your initial system failed to find in the first place, because computers are just really bad at finding those things. And this is what we refer to as the parrot attack. So this served as the basis of one of my doctoral students' dissertations and became a pretty well-known strategy for attacking these systems. And so then the way that we stopped this was that we ran iteration on Parrot. And so basically what you do is you run your first de-identification model, you train your first de-identification model. And then what you do is you say, okay, well, here's all the false negatives. And I'm going to reorient the training of the model again to highly focus on those things. And I run the whole thing again. And then we keep doing this over and over and over again until computers can no longer tell the difference between the real and the fake information. And it just turns into noise. So this is how we built this notion of like how we got comfortable with natural language processing for de-identification. And it's what we now use over at Vanderbilt. So then the question became, all right, so I said earlier that we're trying to get value out of the data. So it's not enough to just make the data accessible. You really have to say, why is it useful? And a lot of you who work in machine learning, I don't have to tell you what the value is, but a lot of other people have a lot of questions about whether or not found medical records data is actually useful for anything, or if it's just going to be an artifact of billing. And so I'm going to highlight a couple of the researchers in the Data Science Center over here, just to give you some illustrations of things that we were doing over the last 10 years to really justify why medical records data should be reused. One of the highlights is Tom Lasko's work, who I'm showing on this slide. And Tom had what I think was probably the first paper on deep learning and the reuse of medical records data over a decade ago for computational phenotyping was what he referred to it as. And so they were trying to take data that was like uric acid and look at laboratory measurements over time and then turn it into a visual component and then use deep learning strategies to give you patterns within that data. Okay, and what that allowed them to do was create richer representations of phenotypes and subphenotypes, as well as develop correlations with outcomes for these patients that hadn't been observed before or hadn't been characterized before. More importantly, or what I think was more important, was that they started looking at some of these signatures for various labs associated with people who ended up with cancer, particularly breast cancer. And so Tom then had this paper that said, you know, if this works, you may be able to have biomarker testing in silico. Obviously, you want to have the ability to do this within blood and check for novel biomarkers. But it turned out that a lot of the data in the EHR for patients that you had enough data on, you could start to do this type of forecasting. A different way to think about how to use the medical record was coming back to the natural language. And so I'm going to highlight some of the work of Jijun Yin. And Jijun got really fascinated with what is it that doctors and patients talk about? And why is it that the patient's voice isn't really taken into account when building these machine learning models? And so Jijun got really interested in looking at patient portals and reusing the data out of the patient portals to pull out the semantics of what people were saying. But more importantly, he started looking at the sentiment of how they were saying it. And what was really fascinating about this was that he got really interested. He had seen some of Tom's work as well. And he's like, well, I want to understand if a patient is going to stay on a prescription regimen for the time that they're supposed to. So for example, when a patient underwent double mastectomy, they were going to be prescribed something like tamoxifen or some type of a hormone replacement therapy for up to a minimum of 5 years, right? And he said, what's the chance that somebody's going to stay on that regimen for 5 years? And so he looked in the diagnosis, like, are they having side effects? And it was like that helped to a certain degree. But it really wasn't until you started looking at what the patients were talking about that you had a better intuition into whether or not they were having a hard time, or whether or not they were struggling emotionally or financially. And that gave us a much stronger indication of whether or not they were going to discontinue their medication. So he's done this also type of this analysis has also been performed using data like social media data, but also like more health structured forums, health media forums like breastcancer.org. What was really interesting about this was that the personality types that gave you a better indication of whether or not somebody was going to be successful was things, and you can see it like jump out at you in this plot to the right, where you can see somebody who was considered to be excitement seeking or outgoing. That type of a personality structure would indicate pretty strongly that they were going to stay on that regimen. The overall, the strongest hit that we came out with was whether or not somebody had a narcissistic tendency, which was really quite crazy. And then we started talking with sociologists about why this might be the case. And the sociologists were like, this makes sense to us because it's the personality type that says, I don't want to fail. And we looked at what people were saying, and it had to do with like their fear of how they would present themselves in society, and this notion of they didn't want to be a failure in the face of their loved ones or their children. And so they were going to make sure that they made it to the end of this regimen, which was their very different type of personality trait than people who were constantly concerned with how their body was reacting. These people who had this tendency to push through, like it was really, really impressive to see that they would make it. One other example, and what I wanted to highlight here was that it's not just what happens to the patient or the patient's way of interacting with the physician that mattered, and that organizational structures mattered. But we could only get this when we started looking at the way in which the medical record was used. So this is Yu Chen's team. And one of the things that they had shown was that the way in which sets of care providers came together to provide care to a patient gave an indication of how long they might actually be in the hospital. And so this was a paper that was published in JAMA 4 years ago, where we showed that with respect to patients post-trauma, that you could see that the one type of an organizational structure that coalesced around patients that seemingly had no other indications, like they were not different in their comorbidities or their demographics. We could see that one type of social structure around how they were cared for was getting them out of the hospital almost 1 day faster than the other patients. This is the value argument with respect to care for us. Okay, and these were structures that were learned by looking at who touched the medical record. So we turned it into one large social network graph and then did an analysis on that graph over time. And so this is kind of led to the phenomenon of, could we understand how healthcare is actually applied as opposed to how we think it's being applied by looking at how the medical record is utilized, right? So this allowed us to discover certain bottlenecks and allowed us to make recommendations for resource allocation, but it also demonstrated for us one of the challenges here, which was that these are not natural organizational structures. And when you go to talk to hospital administrators about, look, this org structure is working, this one's not, they go, we didn't design either of those organizational structures. So how are we supposed to evolve the system from structure A over into structure B? That is for us one of the great challenges. Okay, so that was we were demonstrating, what you could do with this type of data. And so then the question was, well, how do you do this outside of Vanderbilt? How do you do this on a bigger and better level? And so this is where I say, there's safety in numbers. And you have your process, and that process works locally. And you then say, hey, this is what I see. What do other people see? And so now you want to go to all different sites and you want to run the entire process again. You want to test the robustness of your algorithm. Okay, so as we were doing this, this was when the NHGRI created what was known as the Electronic Medical Records and Genomics Network. And this started back in 2007, and it's been running ever since. And one of the things that Emerge did was that they started building reproducible computational phenotypes for the reuse of EHR data. And so you would say, hey, here's what type 2 diabetes diagnoses look like at Vanderbilt. What do they look like over at Northwestern? And then what does it look like over at University of Washington, right? And then we said we need to have an exchange of these computable phenotypes, but there's no real simple way for specifying this. It turns out we even did try to do this with markdown languages like Drools at the time with a JBoss engine to run it all. And it didn't take off. It was just too difficult to implement. So what everybody asked for was just a knowledge base. And so this was what became known as PhiKB. And so PhiKB would tell you, here's the algorithm for a particular phenotype and how well it worked at 5 different sites that implemented it. And here's how they tweaked their algorithm locally to make it work. So more recently, what we've seen is that the NIH said, cool, this is all working really well. How do we really ramp this up at scale? And this is what became known as the program that was just revealed about a month ago, which is the Bridge to AI program, which is this program that's now going to be creating 4 very large data sets that are going to be used for artificial intelligence and machine learning. And where this is focused is on broader data, right? So we've seen examples of DNA and more structured information like medical records, maybe some socioeconomic status, but we want to see how could we get clinical trials information in the mix and all of the other stuff that we're just not using at this time. So could we get retail purchases? Can you get social media data? Can you get people to contribute their fitness records? What are their lifestyle decisions? That's the broader data that we're starting to see integrated. And then you want to get it from a parent, but then you also want to get it from the children as well. And you want to see like what how things evolve over time. And this is really what we're doing over at the All of Us program. And so All of Us kind of became if you look at the evolution here, it's like, what did we do at Vanderbilt? Then what did we learn at the Emerge network? And now what are we trying to do on like a nationwide scale or a broader nationwide scale? And for those that haven't seen this, what we're doing at All of Us is we're basically collecting everybody's medical records. We're asking for 1 million volunteers. We're already at almost 500,000. And they're providing their medical records data, biospecimens, as well as they're responding to surveys and providing, we have a cohort of about 25,000 people who are wearing Fitbits. So there's a public view here, which you can see here. And this is similar to what we built at Vanderbilt, where we were allowing people to query for just, who had which particular combination of diagnoses. And so you can drill down into the distribution of diagnoses or the distribution of medications, and then you'll be able to stratify this a bit. We also we partnered with Verily and with the Broad Institute to put a researcher workbench in place. So that people can do analysis using your standard Jupyter notebook. And so I'm not going to show you screenshots of this. You can log into the system to see it, but it'll look like a Jupyter notebook. The more important part for what I was trying to communicate here is that we again did a tiered level access model. So we have our public use system. You can get access to summary statistics without logging in. We rounded all of the results so that people couldn't triangulate against patients given their queries. And then we created these sandbox environments that I was alluding to. And it's all sitting out on Google Cloud with a Terra basis and Jupyter notebooks sitting on top of Terra. And we created 2 different environments. One is what we call the registered tier, where it's anyone currently at an academic institution that enters into a use agreement with us. This is kind of in its beta form because we're expecting to expand out to citizen scientists starting within a year or so, maybe 2 years. But this was data that we confirmed had a low risk of re-identification. And then more recently, earlier this year, we released the controlled version of this, where this is not going to be out for everybody to access. This is only going to be within trusted institutions. But we've already done 100,000 whole genome sequences, and the studies on this are currently ongoing. And I get a lot of questions about, well, what did you do to the data? And I can't go through all the details yet, but this being recorded, you can always go back and look at this at a future point in time. We're about to publish a paper on this. And what you can see is that in the registered tier, what we did was we did things like date shifts within -1 and 365 days. I will tell you, we removed COVID information from the participants because we didn't want it to break the date shift. We generalized information up to the US state. We generalized certain highly minor racial groups, sex, sexuality, education, like this stuff was rounded out. You'll notice that if you go into the controlled tier, you're going to get much more detail than what you would have gotten within the registered tier. But in both situations, the National Institutes of Health has designated both of these as non-human subjects research. But we've recognized that given the whole genome sequences that exist over in the controlled tier, we wanted to have a bit more oversight on this. And so this resource has been used for a number of investigations so far. We're starting to see the resource used to support analyses into diversity with respect to outcomes. And the reason why we're interested in this is that the goal is to make all of us a much more diverse research cohort than what you might have had beforehand. Now, when you do that, and you might have had this on your mind before, the notion of applying de-identification, it tends to hide information on small populations. And so you have a situation in which there's not many transgender individuals, you choose to hide the data. You don't have many Pacific Islanders, you're going to hide their data. You don't have many people from rural settings, you're going to hide the data. So what this means is that de-identification, it tends to be useful when you have data of sufficient size, but when you don't, you run into this problem of the privacy utility trade-off, where this is what your typical trade-off would look like for a majority population, but in a minority population, it's a much steeper trade-off. And then if you end up in a super minority population, it's even worse. But in reality, it's even worse than that, in that you're not starting at the same levels of utility out of the data to begin with, so that when you try to impose the same level of privacy on everybody, you end up with levels of utility that are substantially worse for these minority and super minority populations. So this kind of begs the question of what's fair, and this is goes towards the question of how do you do algorithmic fairness here, right? So we had this push towards diversity. We didn't want to try and be in this situation, and so we had already recognized that there was a big middle-aged and white basis towards a lot of the data sets that were already out there, and so for all of us, we made a push so that over 50% of the population is derived from populations of underrepresented groups in biomedical research. We're running out of time a little bit, so let me skip over this. And so as we were doing this, the NIH started to make a push to increase diversity, not just in the data, but in terms of the people who were actually analyzing this data. And so this is what we've been doing within all of us as well, where we've been reaching out to historically Black colleges and universities, as well as minority serving institutions, to get them trained to work with data and become involved in doing this type of machine learning work at scale. We did that to a little bit in the context of all of us, but the real big program that's doing this is the program I'm involved with, which is called Aim Ahead, where we now have over 20 pilot projects at various institutions around the country, 20 researcher fellows who are being trained by the program, and 20 leadership fellowships that have started up, and we've just started year 2, so this is going to continue to get larger. If you want to know more about Aim Ahead, then I would encourage you to go to this website. Just go to aimahead.net. We're always looking for mentors, and so you're more than welcome to join up. And with that, I'm gonna close this out and say, like, there's a lot of people who are involved in all of this work. This is only a handful of them. And so I will thank all the funding agencies that have been involved with this work for over the last 15, 20 years.